Dear students, today we will discuss the chirality in alliance and the spirals. Those compounds which not have the asymmetric carbons or stereogenic carbons, though it shows the optical activity. This optical activity where no stereogenic carbon is present. Okay, stereogenic carbon is stereo center where the carbon has the four different group. Okay, we have such type of example ABCD where the carbon has the four different group attached and therefore it is a stereo center. Okay, the compounds are which not have the stereo centers also show the optical activities. Among these compounds, the allenes, spiranes, biphenyls, and other types of examples is there which have not the stereogenic center or stereo centers. This chirality of these compounds, okay, where no stereo center is present, is explained on the basis of axis of chirality and plane of chirality and helicity. Okay, by using this type of chirality, okay, this compound not contain the stereo center or stereogenic center will be explained its optical activity on the basis of axis of chirality, plane of chirality and the helicity. We have the first compound, that is allenes, spiranes and the biphenyls, where axis of chirality is present. On the basis of axis of chirality we will discuss the allenes, spiranes and the biphenyls. We have such type of chiral carbon is there, stereogenic carbon is there, and when we replace this carbon with such group or with C single bond C group, then elongation of tetrahedral carbon takes place when you replace this. Okay, instead of this you take this C double bond C, then A B. Okay, instead of this you have the C double bond C, and all these groups are attached to this. Okay, therefore A D and AB. Okay, therefore elongation of tetrahedral geometry takes place, and such elongation observed in, okay, this is the one of allenes types. The such elongation of tetrahedral geometry is present in allenes, spiranes and the biphenyls, and therefore such elongation produces the axis of chirality. Okay, if such elongated tetrahedral carbon if you found, those compound is considered as a axis of, due to axis of chirality it shows the optical activities. Now we will discuss the allenes. Allenes, there is a such type of double bond is present. Okay, such type of compound is means the allenes. C double bond C and C double bond C. At the both ends there are the groups. The condition for the optical activity in allenes is at this terminal allenes. Okay, this is this functionality as allenes. At this terminal allenes, the group attached on this carbon should be different. The group attached other terminal carbon should be different. Okay, if these groups attached to first carbon if same as the last carbon, it's not effect on the optical activity. If these two groups if same, then also molecule shows the optical activity. Okay, condition is what? This terminal carbon should have the different groups. This carbon should have the different group. If both these two AB group is same, it doesn't matter. It gives the optical activity. But condition is this carbon has these two groups should be different, and this carbon, these two groups different. If these two carbon have the same group, it's even though it is the optically active compounds. But this is the general formula of the allenes. Among these elongated tetrahedral type geometry, the compounds are allenes is one of the compound, okay, which came under the elongated tetrahedral geometry, and then spiranes, then biphenyls. Okay, there is a elongation of the tetrahedral carbon takes place. Okay, if your allenes is looks like that, your biphenyls is okay looking like that. Okay, there is AB group is there, AB group is there. There is again the elongation of tetrahedral takes place. The spiranes is like that. Okay, these are the spiranes where the elongation of this tetrahedral group takes place, and in such compounds, allenes, biphenyls, okay, these are the biphenyls, and in spiro compounds, there is elongation of tetrahedron takes place, and such compounds is optically active due to this elongation. Axis of chirality is produced, and these compounds are the optically active due to there is a axis of chirality is present there. Okay, this is about these three compounds. We can explain. There is a axis of chirality is present, and due to axis of chirality, these compounds are optically active compounds. Let us start with the allenes. We have seen the allenes. One of the condition is there. Allenes, the carbon should have the different groups attached to it. For this, we have one example is there. Okay, if these two groups if present in a same plane, then a plane is passed, and therefore plane of symmetry is there, and therefore if these two groups present in one plane of symmetry is there, therefore it should be not optically active, but these two groups are not in a plane. Okay, so this blackboard, all these things in blackboard is in a plane. Outside the plane, that chalk is the outside the plane, and inside the plane. Okay, therefore this CH3 group is along the plane. Okay, vertically it is found vertically, and this CH3 and hydrogen is the like that. Hydrogen is pointing towards observer, and the CH3 pointing towards the outside, away from the observer. Okay, like that situation is there. CH3 hydrogen and CH3 hydrogen. Okay, this three CH3 hydrogen is the like that present, and the CH3 this hydrogen is the presentation is like that. Okay, therefore when if suppose case is there, and then if you pass the plane, this plane is passed between these two, and in between the, okay, like that situation is there. These are the looking like that, and these are the like that. Okay, like that situation is there. Okay, plane is passed. When plane is passed, it divides this molecule in equal two parts. Okay, if suppose it is different group is there, it has different group. Suppose hydrogen is there. In such condition is also, when you pass the plane through this molecule, it not divides these two. It divides the plane of symmetry is there. Okay, because this CH3 and hydrogen is the planar one. Okay, like that one, CH3 and hydrogen. Okay, these are planar, and these two are the like that. Okay. When you pass the plane is past CH3 hydrogen. Okay, this CH3, because these are present along the plane. You pass the plane, and these two CH3 is present like that. And when you pass the plane, CH3 equal, dividation is CH3 is there, and plane is past CH3, first CH3 hydrogen, and in between the CH3. Therefore, such condition, your molecule is also not optically active. The both terminal ends should have the different groups. Okay, if suppose it is having the hydrogen, and when you try to pass the plane, it not divides these two molecule in equal halves. Okay, therefore the condition is that terminal carbon carry the different groups. Then your alane should be the optically active. These two groups should be the different. Okay, we have seen that this CH3 is the planar one. Okay, like that along your board. Okay, this CH3, and this is the this CH3 is looking like that. Okay, like that you can show like that. Okay, and the second other, this is the like looking like that, and this is the like that. Okay, like that situation is there. This is the along the plane, and this hydrogen pointing towards you, CH3 away from you, and this is one plane. CH3 and hydrogen is present along the one plane. Okay, this CH3 is present along the one plane, and this is the plane present like that. Okay, like that situation there. Okay, one is present at the one plane, and when you pass the plane through this, okay, this CH3 and hydrogen, then at the one CH3 and the CH3, you pass the plane. Okay, this along this there is a CH3 and hydrogen. Along this there is a CH3 and the hydrogen. When you pass the plane among this, okay, in between this, then you found that if it is same one, though it is different one, if it is same one, then it's divided into equal to halves. Therefore, at the terminal carbon, your group should be the different for the optical activity in allenes. Okay, in allenes, stereoaxis is produced, or axis of chirality is there. It means that there is a stereoaxis is there. This stereoaxis is produced because there is a elongation of tetrahedral takes place. Normally tetrahedrons we have shown like that. Normally tetrahedrons was like that. Okay, if tetrahedrons like that, due to this there is elongation takes place, and due to that elongation there is a axis or stereoaxis is present. Okay, stereoaxis is present. Okay, if you replace if you change the CH3 and hydrogen, okay, by breaking the bond, if the hydrogen will go at CH3 and CH3 will come at the hydrogen, then it gives the another in isomer. Therefore, in this such type of isomer is present by replacing the groups. Okay, by interchanging groups, new enantiomer is produced or new isomer is produced, and due to elongation of this tetrahedron geometry, such type of compounds can be explained on the basis of stereoaxis, where stereoaxis is produced due to the elongation of tetrahedron geometry, and this molecule we can explain on the basis of axis of chirality. Okay, this is the structure of the alliance. When you represent alliance in a, okay, suppose we have a compound, like that compound is there. Okay, these are along the plane, and this is the outside. This hydrogen is the outside the plane. This is the chlorine. Okay, pointing towards the our observer. Okay, when you try to in Newman projection formula, okay, when you try looks from this side, you found that the chlorine is at left hand side. Okay, such situation is there. Okay, this such situation is this chlorine and the hydrogen is looking like that, that chlorine and the hydrogen, and when you observe there, when you observe from this, the chlorine and the, okay, that is a chlorine one, that is a chlorine one, that is hydrogen one, and when you observe from this side, then chlorine is at the left hand side and hydrogen will be right hand side, and this is the is vertical line. Okay, therefore the chlorine is at the left hand side and that hydrogen is like that side, and this hydrogen is vertical and that chlorine is the vertical. Okay, then when you pass the axis, okay, that is stereo axis is there, sorry, not that stereo axis is there and C2 axis is there. Okay, though C2 axis of symmetry is present, number of compounds, it shows the optical activity. Okay, axis of symmetry is present. It means it's having the optical activity or not. Okay, C2 axis of symmetry not alters the optical activity. If it is present, it may show the optical activity, or it may not present, it show the optical activity. Okay, this compound has the C2 axis of symmetry. When you rotate this molecule, you will obtain okay, we have shown like that, chlorine, hydrogen and chlorine. Okay, 1, 2 and 2, and when axis is passed through C2 axis of symmetry, okay, that rotation, this becomes will came at that point, this will be go at that point. Okay, like that way you can obtain. Okay, okay, like that you will obtain the equivalent orientation, and the C2 axis of symmetry is present in alliance when your compound is type the AB C double bond C. Such type of compound is there, and that compound shows the C2 type of axis of symmetry. Therefore, asymmetric word, okay, asymmetric molecule, where we apply, where it is optically active one, and which it does not have any axis of symmetry, any kind of symmetry, then it is considered as the asymmetric molecule. Asymmetric means no any kind of symmetry. But in such other type of optically active compounds where the C2 axis of symmetry is present, okay, all other types symmetry is present. If plane of symmetry is present, your point of symmetry is present, alternating axis of symmetry is present, then molecule is optically inactive molecule. But if C2 axis is present, then your molecule should be may it optically active or not, but in some optically active molecule there is a C2 axis of symmetry is present. Therefore, asymmetric where we use asymmetric means that there is no any kind of symmetry. Okay, therefore in this molecule there is a C2 axis of symmetry is present. Therefore, we not consider this molecule as a symmetric molecule. Okay, when C2 axis of symmetry is present and your molecule is optically active, then you consider it as a disymmetric molecule. Such molecule is considered as a disymmetric molecule. Okay, disymmetric molecule. Okay, therefore we have not used asymmetric molecule or instead of chiral one, we not use asymmetric molecule because in this molecule some symmetry is present, C2 symmetry is present. Though it has the C2 symmetry, it shows the optically activity. Okay, some compounds it shows the C2 axis of symmetry. Okay, but if all these groups in alliance, okay, A, B, C, D, okay, all these group is different or any three group is different, then this molecule not show the C2 axis of symmetry. Okay, if A, B, C, D, okay, if after rotation A due to the B position, B will take the A position. Therefore, after such kind of C2 axis, there is no C2 axis is present in this. If all these groups is different or any three group is the different, then such type of C2 symmetry is not present in alliance. But the molecule is AB and AB type, okay, AB C double bond C double bond C AB type molecule is there. Then this show the C2 axis of symmetry. And if all these groups are the different, then it is not show the C2 axis of symmetry and the molecule is perfectly asymmetric. Then you call this that molecule is a asymmetric molecule because this molecule not have any kind of symmetry. Okay. Then orbital representation of alliance. Okay, alliance has the two double bonds. Okay, near double bonds. Okay, this alliance has the such type of double bond is there. And the one of the group of the carbon is away from this carbon, and one is the present at the place. The center carbon is the sp hybridized carbon, and this carbon, okay, where it is a sp2 hybridized carbon, and we know that if sp2 hybridized carbon is there, it is a trigonal planar molecule. Okay, its geometry is trigonal planar, and if it has the sp hybridization, its geometry is the linear. Okay, this carbon has the pi the p orbitals. Okay, these two p orbitals are perpendicular to each other. Okay, these two p orbitals perpendicular to each other. Therefore, at one carbon, it show the vertically C double bond C. Okay, vertical p bond form the C double bond C, and the other, okay, this and these two are the perpendicular to each other, and next carbon has the perpendicular pi bond. Okay, parallel pi bond to this, because for the formation of the double bonds, p orbitals should be parallel to each other. Okay, this parallel form the double bond, and this parallel form the double bonds. Okay, like that way, there is an orbital representation, and its geometry centrally sp2. Sorry, sp2. Your terminal carbon is the sp2, and the middle carbon is the sp, and the such type of their pi bond is formed. Now we have one compound is that is the our alane is there. And when you increases the bonds, okay, more than 3 bonds, 4 bonds, 5 bonds, okay, more than 4 or 5 bonds is there. Okay, that is called as the cumulative. Okay, if you increases the more than 5 bonds in this skeleton of the alliance, it's called as cumulative 1, 2, 3, 4, 5 bonds. Okay, if you add the a bond is there, therefore A, B, C, D's are present in one plane. Okay, therefore due to present in one plane, it shows the geometrical isomer. Okay, and when you add the another C double bond C, okay, 4 C double bond C you add, then its nature is looks like the alliance. Okay, where AB, one of the terminal show the planar AB, and other is that shows the three-dimensional AB. Okay, one is to pointing toward the observer, other is the back side of the observer. Okay, therefore if odd number of C double bond C is the in cumulative, then it show the geometrical isomer. Okay, geometrical isomer when you can see when this ABCD is the planar one. Okay, if it's not planar one, it not show the geometrical isomer. Okay, if odd number of double bond is there in cumulative, then it show the geometrical isomer, and if even number of double bond is there, then it is optically active, and its nature is like the alliance. So it looks like the alliance. Okay, when you you increases the double bond in cumulative. Okay, this compound more than the two bonds in alliance is called as the cumulative compound. Okay, and if odd number of double bond is there, therefore it shows the geometrical isomer, and if even number of double bond is there, its nature is looks like the alliance, and it's optically active one. Now if one of the double bond is replaced by the ring. Okay, if suppose our normal alliance is like that. Okay, when you replace this with the such type of ring, such type of ring, then it also shows the optical activity. Okay, all these at this carbon there should be the different group is attached. It also shows the optical. Okay, what we did here, we replaces just one double bond with the ring. Okay, we use the cyclobutane ring. Okay, that is called as the alkylidine. Such compound is called as alkylidine cycloalkane compound. Okay, this compound is called as cyclidine cycloalkane compound. Okay, it is also called as semi-spiro compound. Okay, this is also called as the semi-spiro compound or hemi-spiro compound. Okay. Now if you replace this with the CH3 hydrogen, then CH3. Okay, such compound is the alkylidine cycloalkane compound, and it also show the optical activity as like the alkanes or allenes, and its geometry is not changed when you replaces this double bond, one of the double bond with the ring, one of the ring. Okay, one of the carbon if you replaces by the nitrogen. Okay, such type of compound is there. Okay, nitrogen is there. Okay, that nitrogen carbon is replaced by the nitrogen, and ring, that is the ring is there. Okay, and only carbon is replaced. Such type of compound is also show the optical activity. If suppose when we replaces both the double bond with rings, it is converted into spiro compounds. Okay, it's get converted into the spiro compounds. Again, necessary condition is the what? Your AB at that carbon, at the terminal carbon AB is the different one. Okay, that double bond we replace this ring, and that double bond we have replaced with this ring. Okay, such compound is called as, this compound is a spirane, that is spiro compound is called as spirane compound, and this such spiro compound is also show the optical activity. Okay, if we replace the CH3 hydrogen, CH3 and the hydrogen, okay, therefore this compound is also optically active compounds, and its name is the spiro compound. That compound we call as spirane or the spiro compounds. Okay, this is all about the allenes and the spiranes where stereo center is not present, but it also shows the optical activity on the basis of axis of chirality or stereo axis. That is stereo axis. That stereo axis is produced due to the elongation of tetrahedron carbon. Okay, this is all about the allenes and the spiranes. Thank you very much.